Hello everyone, welcome to multivariate statistics and machine learning. In this video I will discuss how to fit mixture models. In particular I will focus on the EM algorithm, and I will also discuss a link to the k-means algorithm. If you would like to study this from the lecture notes, then have a look at the section 3.5. Okay, so let's get started. So what's the problem? So we have our mixture model. And the mixture model is given by this thing here. So we have a marginal density that is composed of several individual densities, and each individual density corresponds to one class. So we have sum over all k's, and we have a weight pi k times fkx. And this fkx usually has parameters. So this has, if this would be multivariate normal, it would have a mean and it would have a covariance matrix as parameter. And of course pi k is a vector. It's the element of a vector, and this vector pi is also a parameter of these mixture models. So these are our parameters, and we would like to just put them into one little set. So this is our set theta, and the question is now, we observe data x1, x2 and so on. So each of the x's are d-dimensional data, and so how do we estimate theta hat? So what's this? And of course, given that you know a lot about statistical inference, the easy idea that you could have is let's use maximum likelihood. So we assume n large, then we get theta hat ml by maximizing the likelihood. So that's of course a good idea. So how does it look like in practice? So in practice we need to write down the log likelihood function. So the log likelihood function would be as follows. So log likelihood log L of theta. So theta are all these parameters that I mentioned above. Then x1, x2, xn is our data. And that is given by the sum from I to n, from 1 to n, I from 1 to n of log, and then we write down our mixture density. So we sum over all categories from 1 to k, pi k fkxi. So that's our likelihood, or log likelihood, and you can see that this log likelihood looks difficult and is actually not easy to maximize. Not easy to optimize. And the reason is that we have this kind of ugly term here. So we have a logarithm of a sum. And this is unless we have a very small problem with very few parameters, this will lead to trouble, both numerically and even if we could do it. Sometimes we could do these things analytically, but in this case there's no chance that there will be an analytical solution. So what can we do now? And there is an insight that comes from the latent allocation variable formulation of the mixture model. So the idea is now to treat this fitting of a mixture model problem as a missing value problem. Treat this as a missing value problem, and the question is what is missing. So what's missing is the latent variable allocation. So we need a variable k. So k is a vector, and it goes from k1 to kn. So k gives the hard class allocation for each sample xi. So you can see it goes from k1 to kn. So for each sample there we have a value k, and each ki is from the set 1 to k. So if we don't know k, obviously, and in fact when we do clustering we would like to know k, or we would like to infer k. So what we can do is we can treat it as a missing value, and then we can write down the likelihood as follows. So or we can treat it as data. Let's put it this way. So we treat it as data, and then we can write down the complete data log likelihood, and with the complete data log likelihood we have log of likelihood of likelihood of theta given x1 xn. So these are our data points plus the vector k, and now we get a much nicer likelihood, or log likelihood, and that's simply the sum over all samples of the log joint density, and that's pi ki times f ki times xi. So for each sample we know, of course, now which class they're in, and we know the probability of the class, or we have a parameter for it, and then we can estimate theta. So if we know k, we can estimate theta. So if k is known or would be known, we get theta hat ml from this log likelihood, from complete data log likelihood. So that's the thing. So how do we get to know k? And that's actually also easy once we can assume that we know the parameters. So if theta is known, so if that is typically in multivariate normal case, the vector pi, then all the means and all the covariances, then we simply have to apply Bayes' theorem. Apply Bayes' theorem to get k. Or in particular, we don't actually get k, we get the probability of k given x. And that is the probability of x given k times the probability of k divided by the probability of x. So that's Bayes' theorem, and we use this to get the probability of k for each xi. So for each particular xi we get this probability using Bayes' theorem, and now we have the ingredients for the EM algorithm. So the EM algorithm works as follows. It basically iterates between the two steps. So start with random guess. So either we guess theta hat or we guess k, or actually, as I said, we don't use k, we use the probability of k given xi. So what we have is a soft allocation. So the soft allocation is represented by zik, which is the probability of class k for sample xi. So the sum over zik for all k from 1 to k is 1. So we don't get we just don't say that it's class 3, but we get a probability for class 3, and we also get a probability for class 2 and 1 and k. And if it's unique or very strong evidence, then of course the zik will be 0, 0, 1, 0, 0, and where 1 is for the class that is assigned to the sample. So the EM algorithm works as follows. We start with a random guess, then we predict. So we, in the expectation step, so in the E step, impute k in the form of the zik, and it's called expectation because then we also, so it has two parts, impute the latent variables, and then we compute the expected likelihood or expected log likelihood, because that's now interesting, because if we would, the complete data likelihood assumes that we actually know what k is, so it's either in class 3 or in class 2 or in class 1. But if we don't know if we have just a soft assignment, so this is because of the soft assignment, we compute the following function. It is usually called Q, and Q is the likelihood function, but it's the expected log likelihood function. So we have our data x, we have theta, and that's, we sum over all samples as in the normal likelihood, but then we also average over all the class probabilities. So for each sample we have k probabilities given by zik, and then we just write down the complete data log, like log pi k f k x I. So that's the expected log likelihood, where the expectation is over the soft assignment. So this is why it's called the E step, because we take this expectation. And then we have the M step is for maximization, so maximize Q theta x to get estimates theta hat, and basically we get pi hat, we get mu k hat, and we get sigma hat. That's it. So that's the EM algorithm, and we of course iterate. So step 4 would be iterate until convergence. So if we use the Gaussian mixture model, this leads to very simple formulas. So I'll show you here. So these are the formulas for a normal mixture model. So what you see here is in the E step we impute the zik, which is simply, you can see here it's base algorithm. So we have the mixture model here, and on top we have the probability of the component times the proportion of the components. So this is the joint distribution. And in the M step we get estimates for the parameters. So we get estimates for mu, this, the covariance, and so on. And you can see it's basically always a weighted mean. Okay, so that is how the EM algorithm works. Now the question is, how is this linked with the k-means algorithm? So in the k-means algorithm we do this. So we have we assign our samples to classes, and then we iterate by reassigning the samples to new classes. So we compute estimates of the means, and then we reassign estimates of the means, and so on. So that's actually already very similar to the EM algorithm, and it's even more similar if we look into the assignment. So the assignment in k-means looks like this. So we just take the sample xi and put it into the class that is closest in terms of this distance. So if we now assume that we have a Gaussian mixture model where all classes have the same probabilities and the covariances are all the same across classes, and they all have this form that they are diagonal with one covariance, with the same variance. So identical variance, no correlation, and no dependence on groups, so which is quite restrictive, but it's not uncommon to use this model. Then we get this as our formula for the latent class allocation, which is simply basically the logarithm of the of the base posterior probability, and it turns out it looks very much like this assignment. And of course this is now the logarithm of the soft assignment, but what would we do to assign classes from the soft assignment? We simply take the one that has the highest probability. So this is what you do in k-means, only that you don't think that this is a probability or log probability. So what we do, we take the highest one, and you can see the difference between this and this has a minus. So taking the maximum of this log zik is the same as taking the minimum of this squared distance from the means, because the sigma is of course just a scale factor. Therefore, now we can actually understand what k-mean is doing, namely it's providing a hard classification for a very simple or restricted Gaussian mixture model. So that's an interesting connection. So finally, in conclusion of this lecture, let us briefly look into how to choose number of classes. So in k-means we decided to use the between class variation and within class variation. We could do this as well, but since we are in a likelihood framework, we can do other things, including the BIC that we discussed last term, or AIC. So I've written down these criteria here as well. So what we do, we compute the log likelihood, and then we penalize the model for the number of parameters. So the more groups we have, the more we penalize the model. And there's a program that we're using in the mclust in R, and in mclust the BIC is defined in a different way. So basically with a minus sign. So we have to sometimes we have to minimize the IC, but in some programs we have to maximize BIC, but that's clear from the context. So let's look at an example. So here we have our iris data set again, and if we run this with 3 clusters, so these are just a scatter plot for the 4 variables, and if we run it and then compare the classification obtained by the Gaussian mixture model with the actual classification that we know, we see that there's basically no misclassification, at least compared to the k-means. It's much better. So only this type of flower is misclassified slightly. So it's normally it would be 50-50-50. So we have, so these are the true classes, and these are the classes that we have that the algorithm thinks is true. So, and the other question, so this is doing a very good job, but this is of course specifying that it's 3 classes. So if we look at the BIC, how many classes are supposed to be there in this model? And you can see here that the BIC is largest for 2 classes actually, and but it's almost as good for 3 classes. So the 3 classes, they provide a reasonable explanation. Actually 2 classes also provide a good explanation. Okay, so that's it for today. You will do this analysis yourself in the worksheet, by the way, so that you learn how to actually analyze this data and other similar data sets yourself. Okay, that's it for now, and so see you in the next video. Bye bye.